Hi everyone, let's start. Today we will discuss the most misunderstood concept that I would say decidability. Let me tell you how we are going to proceed in this decidability because we only have few hours, maybe two classes we can take in decidability. So we are not going to go through any proof that is I would say that okay, so we will basically not go through any proof anyway, and from gate point of view we will study. So all the questions that have come in the gate exam, those also I will solve. So every question, every single question in the gate exam or in TIFR exam, so in these exams, all the questions that have come from decidability, okay, so those we will solve. And I will discuss Rice theorem. So this Rice theorem we will discuss, and some other points that I want to basically to understand this decidability, some other points that we need to discuss. So those we will discuss. So you can see that strictly from gate exam point of view I am going to discuss these topics. Okay, I am not going to go into the details of unnecessary things. Only those things we will see in the detail, that from where in the gate exam they can ask questions. Okay, so this is the point. Now let's start this. You can share this video right now. If any of your friend is also preparing for gate exam, then you can share this with them so they can also join, if you know someone who want to study decidability. Let's start. So first let me just tell you the behavior of Turing machine. We are not going to actually take the examples of Turing machine, but we need this behavior. What is the behavior of Turing machine? You already know the finite automata and all other things. So what is a finite automata? That you know, you have some set of states and you have a, this is your basically you can say input tape. This is your input tape. Okay, on this input tape we give the string, some string is there, and this is our finite control, this set of states. Basically this is called finite control. Okay, so this is your finite automata that you already know. We can read a symbol, and basically we can only go from left to right, and we can only read the symbol, we cannot write basically. Okay, so this is the this is the behavior of finite automata, you know. Now similarly, you know PDA and all these things. We will see what is Turing machine. In Turing machine, similar to finite automata, we have a finite control. So this is our finite control. Okay, and this Turing machine is basically a machine similar to finite automata. Okay, similar to finite automata, we have some set of states, and so this is called finite control. And we have initial state. This is our initial state, and okay, I will talk about what is a final state and all these things I will talk about. But you have initial state, some finite set of states you have, and here you have tape. Remember, this is not input tape, this is tape. Okay, this input tape is a different thing, and this tape is a different thing. Tape is a data structure. Of course we do not study this tape in our data structure subject, but this is similar to array, you can say. Okay, this is basically infinite array. You can think like this is like an infinite array. Okay, so this tape is a data structure that we have. Okay, you can say this is a basically infinite memory. Okay, and what we have, so our input string, what we do, this tape we can use as a input tape also. So we can write our input string here. And now what we are going to do, so we are this machine, or you can say this finite control, this is going to read that symbol. And what are the things it can do? So it can read the symbol, it can then write also. So basically it can write also, instead of this A it can write some other symbol, maybe C. Okay, so you can see this is the first difference between finite automata and Turing machine. In the Turing machine you can write also, on your tape you can write also. Okay, second, either you can move to the right or you can move to the left. Okay, so you can see this is second difference between finite automata and Turing machine. You can either move to the right also, and you can move to the left also, that is your choice. Okay, and the third difference is this is an infinite memory. Okay, so this is the third difference, because in finite automata we have finite memory, in Turing machines we have infinite memory. Okay, and also there are many different definitions of Turing machines are there. Okay, so at least 20 or 30 definitions I have studied. Of course, those also include variations of the Turing machine. You already know there are many variations of the Turing machine, multi-tape Turing machine, and many other things. You already know those things. So even in the very simplistic Turing machine also we can have different definitions. For example, either we can allow this input tape to be infinite in both the direction, or we can allow this input tape to be infinite in only in one direction. So basically, this definition also we can use, where our input tape is infinite only in this right direction. Okay, so anyway, this is the Turing machine that we have. So this much is enough. Okay, we are not going to take example, and we are not going to see the transition function of Turing machine. Those things are not required from decidability point of view. Okay, so everything that is required from the gate exam point of view, that is what I am going to discuss. Okay, all other unnecessary things I will not discuss. Now the next thing that we will see is the actual behavior, basically how Turing machine accepts a string. So let's assume this is your Turing machine. So this is your Turing machine M. Okay, and now this Turing machine M, of course this is a machine, so this has a language also. So this is the language of Turing machine, let's assume. Now you know few things that you already know those things. I am just going to discuss them. So the behavior of Turing machine is like this. If you are giving a string, let's assume you are giving a string W, which belongs to the language of Turing machine. Basically this is our Turing machine M. To this Turing machine I am giving a string W. Okay, and this string W is basically this belongs to the language of this Turing machine. This Turing machine has this language, and this W belongs to LM. In this scenario, so you can think of like this W is basically member of M. You can think like this. Okay, so this W is basically of course this W is member of LM. You can think like this, that this W is a member of M. Okay, now for this W, this Turing machine M, what this will do for this W, you can say, okay, for W this will definitely halt. Okay, it will definitely halt, and it will say yes. So both things will happen. It will definitely halt and it will say yes. Now if you give a string which does not belong to, let's assume I give W dash, which does not belong to language of Turing machine. So this W dash is basically non-member of Turing machine. You can think like this. Of course this is not a correct thing, but the point is that this W dash does not belong to the language of this Turing machine. Okay, in that case what this Turing machine will do, so basically for W dash, what this Turing machine will do, it may or may not halt. It may or may not halt. So what things it can do? Either it can halt and say no, either it can do this, or it may never halt. Basically it may continuously run forever. So this loop means run forever, infinite. So this is the behavior of Turing machine for strings. You can see, for those strings which belong to the language of the Turing machine, our Turing machine will definitely halt and say yes. And for all those strings which does not belong to the language of Turing machine, for those strings our Turing machine may or may not halt. Either it can halt and say no, or it may never halt. This is called acceptance. Basically we can say that when our Turing machine is halting and saying yes, so basically we can say that it is accepting W. Okay, this is called rejection. Basically we can say that our Turing machine is halting and saying no, so basically this is rejecting it. Okay, and this is called looping run forever. So in this scenario it is neither accepting nor rejecting. Basically this is looping forever. Of course it is not accepting, like this string W dash is not accepted here, also not accepted here, also not accepted. Okay, but in this scenario we do not know, okay, what is happening, because our Turing machine, you can think like this Turing machine you can think as a black box. We don't know what is going on inside. Okay, we don't know whether this Turing machine is in the infinite loop or not. These things we do not know. Okay, inside this black box, this Turing machine, let's assume this Turing machine has gone into the infinite loop. Okay, then also we do not know whether it has gone into the infinite loop or not. So this is the problem that will introduce undecidability. So anyway, so far I hope that it is clear. If remember, any point of time if you have any doubt, then you should ask. Okay, because this decidability is the most confusing chapter. This is like a inception movie. You will see, this is literally like a inception movie. Turing machine inside Turing machine inside Turing machine. So these type of scenarios we will see. So that is the reason, if anywhere you are confused, if anywhere you have doubt, you should definitely instantly ask. Okay, anyway, so this is the behavior of Turing machine. This is what a Turing machine does. Now we have, depending on the behavior of Turing machine, we can have some different type of Turing machine. So if our Turing machine, let's assume our Turing machine is always halting. You have a Turing machine which always halts, because you can see one thing here. You can see this Turing machine, for members it will definitely halt, and for non-members it may or may not halt. But now consider those Turing machines which always halt, means those Turing machines which always halt. Okay, so for those Turing machines which always halt, for any string like member, non-member, for all strings, okay, for all strings, so those Turing machines we will call them halting Turing machine. Remember, I am going to call them halting Turing machine. This is not halting problem, this is just halting Turing machine. Means this is HTM, means this is a Turing machine which will always halt. This will never go into the infinite loop for any string. Okay, so these type of Turing machines are halting Turing machine. And of course those Turing machines, the remaining Turing machine, okay, like this you can think. Okay, so the second point is all the Turing machines like this. Okay, let me not write it. So you have those Turing machines will always halt, and all the Turing machines. This is basically all the Turing machines. Now depending on what is our Turing machine, you can say that if you have a language L, let's assume you have a language L, and for this language L, let's assume there exists a halting Turing machine. There is at least one halting Turing machine. For this language L, there is at least one halting Turing machine. Then this L will be called recursive. This language L will be called recursive language. And if you have a language for which there is no Turing machine, basically you can say there does not exist a halting Turing machine, then this L is called not recursive. So these are the definitions of recursive and not recursive. Now those languages for which you have there exists a Turing machine, means what it means? It means that for those languages, okay, for which we have Turing machine, of course, the behavior of Turing machine you already know. Means for all the strings that are inside this language L, for those Turing machines definitely it will halt and say no. But for those strings which are not in L, this Turing machine may or may not halt. Okay. So now I am saying that if you have a language L, and for this language L there exists a Turing machine, then immediately we can say that this L is basically RE, recursive enumerable language. This is a RE language. Okay, and if you have a language L for which there does not exist any Turing machine, then for that language will be called not RE. So these are the definitions. Now let me clear few things. This recursive language, you have a recursive language. This is also called decidable language. We will see this. This is also called decidable language. And now this RE language, this is also called recognizable language. Okay. Now also this Turing machine, they correspond to program. See, all the things that I am telling you right now, all these things, the proof of these things I am not talking right now. Okay, because from gate exam point of view, this is not required right now. That is the point. Of course, after gate exam we will discuss all these things in the detailed manner with proof and everything. But right now I am just focusing on how you can solve all the questions, every question of gate exam, how can you solve. Okay, so that is my focus. So now Turing machines, they correspond to program. Okay, and halting Turing machines, they correspond to algorithms. Basically algorithm means Algorithm means a program which will definitely halt. Means this is a program. Algorithm is a procedure which will definitely halt for every possible input. Okay, so Turing machines correspond to program, halting Turing machine correspond to algorithm. So this much. Now okay, let me see the doubts. Is it sir, it won't say yes ever, are we sure, in case of W days? Yes, see here, okay, let me clear. Here, this W dash does not belong to language of Turing machine. So you are giving this W dash which does not belong to the language of this Turing machine. So for this W dash, never this Turing machine will never say yes. This Turing machine may or may not halt. If it will halt, then it will say no, okay, and it will or it can loop forever. But of course, this will never say yes for W days, for this W days. Okay, and for this W, it will always say yes for a member. This W is a member. Okay, so that's why for this W, this Turing machine will definitely say yes. Okay, let me see the next doubt. On W does not belong to LM, we cannot know whether it actually belongs or not. Yes, that we will see. Sir, how can we know that this Turing machine accepts only this much language, as it may go to infinite loop, so we do not know whether this will be accepted or not. See, all these things I will discuss. Now I am just saying, I am just telling you that this is the behavior of the Turing machine. Okay, all your doubts will be clarified as we proceed. Now let me tell you that when we will discuss some problems, there you will see many problems are actually undecidable. Actually most of the problems are undecidable. So all your doubts will be clarified as we proceed. Okay, now so okay, so far so good. So these are the definitions. Okay, now let's see the next point. Now you can see, if a Turing machine is given a string, what can happen to the computation? So to a Turing machine M, if I give you a string W, then what can happen? The answer is this. This machine can either accept the string. Accept the string means it will halt and it will say yes. Yes, saying yes means accept. Okay, so that's why either this can happen, or it can reject the string, means it can halt and say no. Saying no means rejecting. It can reject the string, or it may enter an infinite loop. Okay, so basically the computation never ends. This Turing machine, this box, you can think like this is a black box. This will keep on going on. This will, okay, so this will not halt. So one of these things can happen, as I have already explained. Okay, now what is looping on a string? Looping means infinite loop, running forever. We say that a machine loops on a string if a string puts the machine into infinite loop. Basically our Turing machine, this is basically has gone into infinite loop. Okay, so when a machine loops, it never enters the accept okay, yeah, let me tell you few more things. So actually there are many definitions of Turing machines, but the most popular definition that I have seen, I would not say most popular, but many authors use this definition. So the one of the definitions that we will follow in this lecture, in this decidability lecture, in this definition, our Turing machine is like this. This is our finite control. In this finite control, we have initial state. Okay, in this finite control, exactly one accept state is there. So remember, this is the definition that we are using for Turing machine. In our Turing machine, we have exactly one accepting state. Exactly one accepting state. Okay, so state, this we will call F. So this F is a accepting state. Okay, and exactly one reject state. Remember, similarly, exactly one reject state. What it means? So exactly one we will call it R. So basically in this definition of Turing machine that we will use, okay, that most authors are using, in this definition we have exactly one accepting state and exactly one rejecting state. These states are the only halting states. Remember, so F comma R are the only halting states. What it means, I will tell you. But remember, this is just one possible definition. Of course, there are many equivalent definitions of Turing machine. This is what I am going to use. Okay, now what it means. So yes, this is clear that we have exactly one accepting state. If you want to accept, a string, okay, then definitely you will this Turing machine will have to enter into f. Okay, if you want to reject a string, then your Turing machine will have to enter into r. And remember, okay, f comma r, these are the only halting state. What it means, that all the remaining states are basically looping state. Okay, if you are running your Turing machine, this Turing machine, you are running on a w. Okay, and on this w, if this Turing machine enters into f, once you enter into f, remember this f is a halting state. What it means, once you enter into this f, then you can never go out, and the computation will immediately halt. So this is your state f. Okay, this Turing machine is running, let's assume this Turing machine m, this is running on w. Now when this Turing machine is running on w, as soon as this Turing machine will enter into this state f, or immediately this Turing machine will halt. Okay, the computation will halt immediately. Okay, and we will accept. So basically we don't need to read the complete string. As soon as this we will enter into this state f, we will immediately halt, and we will immediately say yes. So this is the accepting state. Now similarly we have a reject state. As soon as we enter into this reject state, okay, when this Turing machine is running on w, as soon as we will enter into this state r, we will immediately halt, okay, and say no. And if we are never reaching, let's assume this w, this Turing machine m is running, okay, and let's assume that this Turing machine m is never reaching either f or r, then we will say that Turing machine is basically looping. Means f and r are the only halting states. All other states are basically, they are looping states, you can say. If you want to halt, you have to come to either f or you have to come to r. Similarly, if you come to f, then you will halt. Similarly, if you come to r, then you will halt. So this is the point. Now here you can see, when machine loops, it never enters accept state or the reject state. When our machine is looping, okay, when a machine loops, it transitions forever among the states that are neither the accept state nor the reject state. What it means, let me tell you. So if our Turing machine is, let's assume on this w, our Turing machine is looping this m. So m on w looping, let's assume looping. Then what it means? It means that this Turing machine will never enter into this state. Also, this will never enter into this state. In these two states, our Turing machine will never enter when it is this working with w, basically when this is running on w. Okay, so you can say that this Turing machine is basically just looping, or you can in the other states. Okay, from these other state, whatever are the other state, okay, from one state to another, this is just looping. So this is the scenario. So when a machine loops, it transitions forever among the states that are neither accept nor reject state. So this is just to clarify what is looping means in a Turing machine. What is looping means? Next point that we will see. Okay, now when do we say that Turing machine recognizes a language? So the Turing machine recognizes a language L. Okay, what it means? If a Turing machine, this Turing machine has the language, means language of Turing machine is L. What it means? It means that on all the strings that belong to L, on those strings it will definitely enter into the accept state. The strings in L, actually this is strings in L, put m into accept state. And if you are giving a string that does not belong to L, for those strings it can either go to reject state or it can go to loop state. A language is Turing recognizable if some Turing machine recognizes it. So all these things we have seen. So far, if anyone has any doubt, you can ask. So this is the point. Remember, if you have a Turing machine and let's assume that language of this Turing machine is L, then what it means? It means that it definitely means that if you will give a string that belongs to L, if you give this string that belongs to L, for this string definitely our Turing machine will halt and say yes. Okay, and for the strings that do not belong to L, for those strings this Turing machine may or may not halt. That we have already seen. So far we have seen the behavior of Turing machine, we have seen. Okay, if everything is clear, then we will move to the next topic. Now, now let's see. So before we move on, let me tell you, actually I have already discussed about these things in the countability chapter. So first is encoding of Turing machine. Encoding of Turing machine. This we have already discussed in the countability chapter. You can refer to the this countability lecture on our website, on our YouTube channel. So there I have already discussed about encoding of Turing machine, encoding of DFA, encoding of NFA. I said that if you have a finite description, then that can be encoded in the binary format. Okay, so basically if you have a Turing machine, this is your Turing machine, this is your Turing machine, this Turing machine can be encoded into binary format. Okay, so this complete Turing machine, this can be encoded in a binary format, and this I have already discussed, because I told you that a Turing machine is nothing but some things are there, like set of states. Okay, initial state, okay, some sigma, some gamma, final state, reject, this is basically accepting state, this is reject state, okay, transition function, okay, this blank symbol. So these things, basically this is your Turing machine. So you can see Turing machine is a finite description. Okay, similarly this delta is also finite, some set of transitions you have. So you can see everything is finite. This Turing machine is a finite description. Okay, now from this description, what you can do from this description, many things you can do. Either you can draw the diagram. This is just a diagram representation, remember. Okay, whatever we write, like this, whatever we write, that is just a diagram representation. Turing machine is this. Definition of Turing machine is this. Okay, so this finite description, this is our Turing machine. This finite description we can represent using diagram also. This finite description we can represent using binary string also. Like for this, let's assume this is a particular Turing machine. For this Turing machine, either I can make a diagram or I can create a binary string like this, something like this. This we have already, actually I have already talked about it in the countability lecture, but the point is this. So if you have a Turing machine, that Turing machine can be converted, or you can say that can be represented by some binary string. So this is called binary encoding of Turing machine. Okay, for every Turing machine we have this type of encoding. Okay, and now few things you need to note down, that if you remember your this algorithm, in algorithm subject we study something called Hufman encoding. Okay, so there you know one thing, that you are the sender and this is the receiver. So you are sending some message, and this message you are encoding, this message you are encoding. So if you know how you have encoded it, then you also know how to decode it. If you have encoded this machine, then you also know how to decode it. So that is the point here. If we define some encoding for Turing machine, okay, once I define how to represent this Turing machine using binary string, I also know if I have a binary string, if you give me a binary string, let's assume you give me a binary string, then I can decide whether this binary string represents a valid Turing machine or not. Okay, so are you getting this point? In the Hufman encoding, you can see, if I am the encoder, if I am deciding how to encode the Turing machine, then I can also find out very easily, I can also find out by some algorithm whether this given binary string, this is the given binary string, whether this is representing some valid Turing machine or not. Okay, so that is the point. So what it tells you, it tells you that if you give me, let's assume I have decided some encoding. Okay, so this encoding has been decided by me, the encoding for Turing machine I have decided. Okay, so this is the encoding that I will use. This I have already decided. Now if you give me any random binary string, then I have the algorithm, I have the procedure. Okay, basically I have the algorithm or procedure to find out whether this binary string is representing some valid Turing machine or not. For example, if you see this binary string 00000, let's assume this binary string you consider. Of course, this binary string is not representing any valid Turing machine. Okay, so I have algorithm. Okay, to find out whether if I give this string to my algorithm, then that algorithm will say that no, this is not a valid Turing machine. So this is the point. Okay, and from this point you can notice that this problem this problem, whether a given Turing machine represents, sorry, whether a given binary string represents a Turing machine or not, this is decidable. So let me tell you what I am saying. So I am saying that given binary given binary string, if you give me any binary string, okay, given binary string w, if you ask me whether w represents a Turing machine, valid Turing machine or not, okay, so if you ask me does w represents a valid Turing machine, okay, valid Turing machine means basically some Turing machine, okay, okay, if w represents a valid Turing machine, if this is your question, let's assume this is your question, this is the problem actually, you can see this is the decision problem. What do I mean by decision problem? This is a problem for which I can answer yes or no basically, okay. Decision problem is a problem for which the answer is always in yes or no, okay. So this is a problem. Given binary string w, does w represent a Turing machine, valid Turing machine or not? This problem is decidable. I told you decidable means algorithm exists. I have algorithm because I have decided what is the encoding, so I can definitely decide, okay, whether the given string will represent valid Turing machine or not. So this is decidable. I can say that I have algorithm. So now from now onwards what will happen? We are not going to care about those strings which do not represent valid Turing machine. Okay, for example, this string, of course this string does not represent any valid Turing machine, so we do not worry about it, because to distinguish between valid Turing machine and not, we have algorithm. So this is the first important thing that you should note down. So this is a very intuitive thing, okay. If anyone has any doubt, you can ask. Given binary w, does w represent a non-valid Turing machine? This is also decidable. Yes, complement of decidable problem is always decidable. This you might have already studied in your closure properties. If you have a recursive languages, set of recursive languages, they are closed under complementation. So if you give me, given a binary string w, okay, does w not represent a valid Turing machine? Okay, that is also decidable. Complement of decidable is decidable. So the point is basically from now onwards, we are not going to worry about this problem. Okay, like whether whether a given string is valid Turing machine or not. This problem we are not going to worry about, because this is already decidable. Using some algorithm we can do it. Okay, now let's move on. So we have seen what is encoding of Turing machine, and now what we are going to do. So as I told you, Turing machine, they correspond to programs. Means basically for every Turing machine we can write a program, and for every program we can write a Turing machine. This is the meaning. If you have a Turing machine, then you can write a program, and if you have a program, then you can write a Turing machine. This is the point. Okay, now if you have seen this compiler, if you know this compiler is also a program. Of course this is also a program. This is a very big program. So this is also a program. Compiler is also a program. And what this compiler does, yes, this compiler is a program. This basically, instead of compiler I can write that yes, this is a program, and the input of this program is also a program. You can see. So this is a program which is taking inputs, also program. Similarly in Turing machine also. In Turing machine we can have Turing machines for which input is also Turing machine. Now here few things you must note down. Okay, like all the machines that we have, all the machines, finite automata, PDA, DPDA, whatever, Turing machine, whatever, all the machines that you have a machine. Okay, so for this machine the input is always a binary string. Remember, the input is always a binary string. So this input is always binary string. Now the point is, if I want to supply, let's assume I have a Turing machine M. Okay, this is my Turing machine. If I want to supply a Turing machine, then how I am going to supply it? I am going to supply the binary encoding of Turing machine. This is the point. Similarly to this Turing machine, if I want to supply a DFA, then how will I supply? I will send the binary encoding of DFA. But the point is always the machine that we study, okay, all the machines that we study, they will always take the input. Your input is always binary string. So that is the point. Okay, So because your input is always binary string, so the language of Turing machine means those binary strings which it will accept. So those binary strings which it will accept, they are also subset of sigma star. You can see if your sigma is 0, 1. So this is the point. Did you get it? Okay. So because the input is always binary string, so basically we are accepting or rejecting or looping on this binary string. If we are accepting this binary string, then it will go in our language of the Turing machine. So in our language of Turing machine, always we have binary strings. All these things are binary strings. Okay. So all these points that I am telling you, all these are very important points. That's why I am telling you. Okay. Now let's move on to the Rice theorem. Now we will start the actual things that we want to study. So this is the Rice theorem, and the Rice theorem says that any non-trivial property of RE languages is undecidable. Any non-monotonic property of RE languages is not even recursive enumerable. So this we need to see. Let's see. So first of all, what is a property of language? So in this Rice theorem, few things that we need to see. You know, first thing, that is what is a RE language. Remember, RE language, a particular RE language, that is a particular RE language, that is just a language, some set of strings. Okay. Now also there is something called set of RE languages. So there is a difference between these two things. This is a particular RE language, means this is a subset of sigma star, because this is a particular RE language. L is a RE language. And what it means, set of RE languages, what it means? It means that here you have all the RE languages. This L is also here. Okay. And all other RE languages you have here. So this is your set of RE languages. This we will call RE set. So whenever I say RE set, it means set of RE languages. And whenever I say RE language, it means a particular language. Remember, this RE set, this is not a subset of sigma star. Because in this RE set we have languages. In this we have languages. And in this RE language we have strings. Okay. So this is the point. So this is a language. In this language we have strings, and this is RE set. In this RE set we have languages. All things are languages. Every element is a RE language. So this is the point. So whenever I say RE set, it means set of RE languages. Okay. Now the next point. Yeah. So this is the first thing. Now the second thing we will see. So second thing is, what is a property of a language? So property is basically a predicate. If you have already seen predicate in your first order logic, then property is basically, what is the definition of property? Property means a predicate over one variable. Over one variable. This is the definition of property actually. If you have a predicate over one variable, then that predicate is also called property. For example, if I give you px like this, let's assume x is even. Okay. Then here actually this px, this is actually a property. This is a property of x. Of course, here the domain of x. What is the domain of x? That can be, for example, let me give you the domain of x is set of integers. So this is the property. So property is nothing but a predicate over one variable. Okay. If your domain is set of integers, then what you can note? You can note that this property p, this is satisfied by 2, and this is not satisfied by 3. So this is the point. If your domain is set of integers, this is the domain I have given to you. Okay. So this is the case. So this is the property. And now I am saying that 2 will satisfy this property, 3 will not satisfy this property. So this property, I can say this is a non-trivial property. For this property, what I can say? I can say non-trivial property. What is non-trivial property? Non-trivial property means in the domain some elements satisfy and some elements does not satisfy. So non-trivial property means there exists element x who satisfies the property, and there exists element x who does not satisfy the property. This is the definition of non-trivial property. In the domain there is at least one element who will satisfy the property. In the domain there is at least one element who does not satisfy the property. So this is the definition of property. Property is nothing but a predicate over one variable. Like this is your property. This px, x is even. This is a property. And this x is a variable. And the domain of x is, let's assume, set of integers. So this is the point. Okay. Let me take some doubts. So, but sir, we have blank symbol also in Turing machine. Does it make sigma star a subset of tape alphabet? See, blank symbol is not your epsilon. First of all, okay, this blank symbol that we have in Turing machine, this blank symbol is a special symbol to fill all the positions. Basically, this is your tape. Let's assume on this tape, let's assume I am putting this string. Now all the remaining cells, because this is an infinite tape, all the remaining cells will be filled with a special symbol. This b is just a special symbol. First of all, this b is not your epsilon. This b is not an empty string. First of all, that is the point. This epsilon is a string. This is an empty string, and this b is a symbol, a special symbol, okay, which we use to fill all these remaining cells. Okay, so this is the first point. Now, I am not getting your doubt. You are saying, but sir, we have blank symbol also in Turing machine. Does it make sigma star a subset of type alphabet? Sigma star can never be a subset of type alphabet. Sigma star, what is this? If you see sigma star, let's assume your sigma is 0, 1. This is your sigma. Then sigma star is basically set of all strings over 0, 1. This sigma star is actually in set of all strings over 0, 1. And what is your type alphabet? Type alphabet is gamma. Okay, this type of alphabet can have 0, 1 and blank symbol and some other things. I can say that sigma is subset of gamma. Yes, that I can say. Definitely sigma is proper subset of gamma. Yes, this is guaranteed. Yes, that is also, yeah, that is also correct. So I can say that sigma star is proper subset of gamma star. That is also correct. No problem. Because you can see in gamma we have sigma also, like 0, 1 is also there, and this blank symbol is also there. See, right now to all the other students, I would like to say that I am just answering his doubt. Okay, so you don't have to worry about it. If you did not get it, then just forget about it. Okay, not required. Sir, but in RE set there are countable languages, and hence we can also represent each language in binary string, and hence make RE set a subset of sigma star. Yes, actually, Naim, you are right. Okay, so that we will see. Don't worry. So it will also come. Your doubt is nice. So that is also going to come. But I just wanted to tell you the difference between a language and set of language. There is a difference. Okay. So that difference I wanted to say. What you are saying, that is also correct. Like, okay, we will discuss it. Okay. Now, so yeah, we were discussing this property. So you can say this is the behavior. Now let's take one more example. Now in the Rice theorem, if you notice, in the Rice theorem you can notice, first of all, he is saying that a non-trivial property. You know what is a non-trivial property? Non-trivial property means in the domain there exists an element which will satisfy the property. In domain there exists an element which will not satisfy the property. So this is clear, non-trivial property. Okay, RE language, this is also correct. Now what is RE languages? It means our domain is set of RE languages. So that is the point. So from in the Rice theorem, let me tell you, this Rice theorem, in this Rice theorem actually our domain is a set of RE languages. This is our domain, basically RE set. Okay, in this domain we have all the RE languages, L1, L2, all the RE languages we have here. So this is the domain. Okay, and now whatever property I define, that is basically I am going to define for like for languages I am going to define this property. For example, see this property, L is empty. You can notice that, remember, domain is RE set, means set of RE languages. Now if you notice, this property is a non-trivial property, because you can see this property is satisfied by phi. Remember one thing, phi belongs to our domain, so that is why I am taking phi, because this belongs to our domain, because phi is a RE language, so that's why. So p5 is, you can say this is true. Okay, and if I ask you p sigma star is a regular language. Every regular language is RE language. So this sigma star is also element of RE set. This domain, this is our domain. So this sigma star is also element of our domain. Now what is p sigma star? That is false. So hence in our domain I have two elements. For one element it is true, for another element it is false. So I can say this property, this is also a non-trivial property. And this is a non-trivial property of RE languages. RE set means RE languages basically. So if your domain is set of RE languages, then definitely this property is a non-trivial property. So this is the point. Okay. Now, so the definition of non-trivial and trivial property, I hope it is clear. So anywhere, if you have domain, let's assume this is your domain, then the trivial property definition means for all x, means for all elements, either the property is true, or for all elements the property is false. Then this is called trivial property. Means for all the elements, either this property is true for all the elements, or this property is false for all the elements. In that case, we will say that property is trivial. And what is non-trivial, that we have already seen. Non-trivial means there exists x for which property is true, and there exists x for which property is false. So this is the definition of trivial and non-trivial property. Okay. Now first we will actually focus on this is called basically Rice theorem part 1, and this you can call Rice theorem part 2. So this Rice theorem part 2 we will see after some time. Let's focus on Rice theorem part 1 only. Okay, so let's see here. So a property is non-trivial property that we have already seen. For example, is empty. This is a non-trivial property of RE languages, because in the set of RE languages, okay, we have a RE language which will satisfy this, and we have another RE language which will not satisfy this. Similarly, let's see this property. What about this property? See, is not accepted by a Turing machine. If you notice this property, this is trivial property of RE languages, because if you have RE language, if you have any RE language, then for all the elements, like if this is RE language, then definitely for this RE language, this is false, this property, because the definition of RE language says that it is it is accepted by some Turing machine, at least one Turing machine. So for every RE language, this property is false. And that's why we can say that this property is trivial property of RE languages. So this is the definition of trivial non-trivial property. Now what is Rice theorem trying to say? Rice theorem is trying to say that this is undecidable, this LP is undecidable. So basically this Rice theorem is saying that if I define this language LP like this, set of Turing machines, remember what it means? It means encoding of Turing machines. So basically in this LP, I have binary strings. In this LP, I have binary strings, and every string is representing some Turing machine. Okay, and now basically LM satisfies P. LM satisfies P. This language LP, this is undecidable. This is our Rice theorem says. So Rice theorem is saying that if you are having a property which is non-trivial property of RE languages, okay, if this P is a non-trivial property of RE languages, if this P, let's assume this P is non-trivial property. So if this P is a non-trivial property of RE languages, then this language LP will be undecidable. Remember, in this language LP, we have set of Turing machines whose language is satisfying this property P. So this language LP is undecidable. Now let's see example. With example, this thing will be clear more. So let's see this. Accepts epsilon. You can see. Of course, this is undecidable problem. This accepts epsilon. This is non-trivial property, because you can see this is a RE language and this does not satisfy this property, and this is another RE language which is satisfying this property. So that's why this is non-trivial property, and definitely this non-trivial property, okay, of RE languages is undecidable. Similarly, accepts an infinite language. This is also undecidable. Why? Because this is RE language. This is RE language. Okay, and you can see this is not satisfying this property, and this is RE language which is satisfying this property. So that's why this is also non-trivial property, and every non-trivial property of RE languages is undecidable. Basically, this language, if I call it L, then this L is undecidable, because in this L, what is happening? In this L, we have set of Turing machines, okay, such that this complete line I can write like this. LM is infinite. This complete line I can write like this. LM is infinite. So you can see this is a non-trivial property, and hence I can say this language L is undecidable. Okay. Now let's take more examples. Yeah, let's take these examples. So let's see, he's saying given Turing machine M, okay, these are the properties. Now let's verify one of them, all of them. He's saying, does LM contain M? First of all, this point, whether this is a trivial property or not. See, you need to understand this. He's saying that given a Turing machine M, does LM, it's like this, language L is like set of Turing machine such that M contains, LM contains M. So this is also this non-trivial property. Why? Because you can notice that this consider this RE language, phi. Okay, you can notice that this phi, if this phi is accepted by Turing machine M, let's assume, of course this for this phi we have some Turing machine, this is RE language, so for this RE language we have some Turing machine M1, let's assume. You can notice that this phi does not contain the encoding of M1, because actually phi does not contain encoding of any Turing machine. Phi is empty set. So this is a RE language which will not satisfy this property. Similarly, this sigma star contains everything. So this is a RE language which will satisfy this property. So basically we have at least one RE language which satisfy this property and at least one RE language which does not satisfy this property. So you can say this containing M, this property is basically non-trivial property, and hence we can say this L is undecidable. Okay, so this is just application of Rice theorem. Is this clear? Let me know. So this is the point. Next he is saying that is LM non-empty. This is also your non-trivial property, because we have at least one RE language which does not satisfy this property and we have another RE language which satisfy this property. So phi does not satisfy and sigma star is satisfying this property. So that's why I can say that this property is also non-trivial property. So definitely this is also undecidable. Okay, next, is LM empty? This is also non-trivial property. Is LM infinite? This is also non-trivial property. Is LM finite? This is also non-trivial property of RE languages. Okay, is LM cofinite? And the definition of cofinite is given to you. Right now we are only talking about decidability, undecidability. Okay, we will definitely talk about the RE, not RE, that also we will discuss. Josefa, right now I am just only discussing decidability and undecidability. So you can see this, is LM cofinite? This is also non-trivial property because the definition is also given. Cofinite means LM complement is finite. So this is the definition of this cofinite. Okay, next, is LM equal to sigma star? This is also non-trivial. So actually all these properties are non-trivial properties of RE languages. So that's why all these properties are undecidable. Okay, so if this point is clear, let's take now let's take this example. He's saying set of Turing machines LM is infinite. Yes, again this is a non-trivial property, so you can say that this language is undecidable. Similarly, this ETM is also undecidable because LM is equal to phi. This is a non-trivial property, so this ETM is also undecidable. But remember, let's focus on this example. What is this example? This is saying that set of Turing machines M has 15 states. This actually, if you see this language and this property, if you see, this property is not a property of RE languages. Okay, this is not a property of RE languages. This is property of Turing machine. Now, how to decide whether a property is property of RE languages or Turing machines? How to decide that? Okay, this type of examples we will cover in the next class. We will cover this type of example in detailed manner. Okay, I will tell you about semantic property. So that definition I will tell you. But right now, the only thing you should focus is that this M has 15 states. This is a language. This is not a language property. This is a Turing machine property, and this is decidable. Why this is decidable? Because I told you that for this Turing machine, if I give you the binary string, this binary string I am giving you, some binary string I am giving you. So because I have done the encoding, so I can also see in this encoding, I will just read the encoding and I will just see how many states are there. Okay, are you getting the point? Let's assume this is my encoding, this is the binary string you are giving me, some binary string you are giving me. So for this binary string, what I will do, I will just look at this binary string and I will check, okay, where I am encoding the number of Turing machine. So number of states. Okay, here I will check how many states we have. If I have 15 states, then I will accept. If I do not have 15 states, then I will reject. So you can see this is decidable because we can write algorithm for this. Just by looking at the encoding, we can tell these things: how many states are there, how many transitions are there, how many symbols in the alphabet are there. Many things we can just say just by looking at the encoding. Okay, if you look at the encoding, then what are the things you can say? You can say number of states. You can directly say number of states just by looking at the encoding. Similarly, you can say number of number of transitions, number of transitions, like, okay, number of input alphabet, number of tape alphabet. So many things. Okay, you can just directly say yes or no, okay, just by looking at the encoding. So that's why this type of problem, this M has 15 states, this is decidable. We can write algorithm for it. Okay, let's talk about the next Rice theorem, the Rice theorem second part, basically this non-monotonic property. Let's see this. What is this non-monotonic property that we need to see? Has greater than 15 states is undecidable. No, all these things are decidable. See, I told you, if I give you, let's assume you have written the encoding. Okay, so Sabrina has written the encoding of Turing machine. Okay, she has her own encoding of Turing machine. Now, so you have encoding, and you know that if you can encode, then you can decode also. Okay, so that is the point. Now let's assume I give you some random binary string. So this random binary string I have given you, some random binary string, something like this. Okay, now because you have done the encoding of Turing machine, you have decided how to encode the Turing machine. Okay, so you can also write a algorithm, and this algorithm will tell you, basically this algorithm, what in this algorithm you can write down how to find out how many states are there. Okay, so actually, if you remember the countability lecture, there I have actually told you about it. So you can just refer to the countability lecture. There I have said these things. I told that if you have a Turing machine M, and in this Turing machine Q0, many things you have. Okay, delta. Okay, final, this basically final state. Okay, so this is your Turing machine. This is a finite description. And how do we encode it? We encode like this. Let's assume I am giving you my own encoding. In my encoding, what I will do, first I will write, let's assume there are 3 states. Let's assume there are 3 states. Then what I will do, I will write 0 0 0. So in my encoding, if I see 3 0 in the beginning, then it means I have 3 states. Then I will write 1. This is 1. Okay, then I am going to write what are those states. So like 1 is Q0, 1 is Q1, 1 is Q2. Okay, like this. Next I am going to write what is the initial state. So the initial state is 0. Let's assume basically the initial state is this. Next, after that I am going to write what is the final state. What the final state is 0 0. And what is the reject state? The reject state is this 0 0 0. Let's assume like this. So you can see this is my own encoding. This is how I am encoding. Now if you will give me any string, let's assume you give me this type of string, you give me. Okay, then for this string, because I know my encoding, so for this string, just by looking at this string, I can tell you whether this is a valid string or not. Basically, whether this is a valid Turing machine or not. First I will decide that. If this is representing a valid Turing machine, then what I will do, then I will just see the beginning zeros. If there are 5 zeros, then basically it means that my machine has 5 states. So that's why you can see that this number of, how many number of states are there. Okay, all these properties that you can find out just by looking at the encoding. All these properties are decidable, like how many states will be there, how many transitions will be there, how many alphabet symbol are there, how many tape alphabet symbol are there. All these things you can answer just by looking at the this string. Okay, just by looking at the encoding. So like Sabrina is asking, has greater than 15 states, is it undecidable? No, this is decidable. Okay, because whatever string you will give me, for that string I can say yes or no. I will just look at the string, and if it is having more than 15 zeros, then I will say yes. If this is not having more than 15 zeros, then I will say no. So you can say I can always say yes or no. So that's why this is decidable. I am confused in solving question with options like RE or not RE, able to figure out CS. So all these things we will discuss, Ujefa, don't worry. Now let's see the next, that is non-monotonic property. What is a non-monotonic property? So the definition is like this. First I will define monotonic. Okay, so this monotonic property, let me define. Monotonic means that, let's assume you have two set A comma B. Okay, and let's assume that this B is a superset of A. Okay, then monotonic property says that if A has some property P, means if property P is satisfied by A, then property P must be satisfied by B. This is monotonic property. Okay, basically if you are satisfying some property, then your superset must satisfy that property. So this is what is called monotonic property. Remember, if you are satisfying some property, then your superset must definitely satisfy this property. So this type of property are called monotonic property. And now you can very easily find out what is non-monotonic property. Non-monotonic property means there is at least one, there exists A comma B such that A is subset of B, and even though this A is satisfying this property, but this B is not satisfying this property. So this is the definition of non-monotonic. What it means? It means that there is at least one set A, okay, such that this A is satisfying the property, but its superset does not satisfy the property. So this type of property are called non-monotonic property. Okay, so here we can take some example. Like if I give you that, let's assume this 1 comma 2, 1 comma 2 comma 3, and let's assume 1 comma, basically like, okay, consider consider this set. This is your set A. In this set we have 3 elements. Now for this set I am defining a property. Basically for the elements of this set I am defining a property like this: X has basically cardinality of X is basically 2. Now this is my property. You can say P of X means cardinality of X is equal to 2. Now this property is definitely non-monotonic property, because you can see, okay, this is my set A. In this set we have 3 elements, so the domain of X is basically this A. The domain of X is A. Now if I take this element, then this element is satisfying the property because cardinality is 2, but its superset is not satisfying the property. So that's why I can say that this is a non-monotonic property. Okay, so that is the definition of monotonic and non-monotonic. Now let's see what is this Rice theorem saying. Rice theorem is saying that if you have set of RE set, this is your set of RE languages, this is your domain. Okay, so in here you have all the RE languages. Now he is saying that if I give you some property of RE languages, if that is non-monotonic, okay, then every non-monotonic property is unrecognizable. Now consider this property. Let's consider P of L is equal to L is finite. Okay, consider this property. You can see this property is definitely non-monotonic property. This property is actually non-monotonic, and NM means non-monotonic, because you can see this element phi, this is a RE language, and remember, always take elements from this domain. So this is a RE language, this is satisfying this property, but its superset is not satisfying this property. So that's why this is a non-monotonic property. If I say L is infinite, this is a monotonic property, because if you take any RE language, let's assume you take a RE language L1, and you take another RE language L2, such that L2 is superset. Definitely if L1 is infinite, then its superset is also infinite. So this is a monotonic property. Okay, for example, consider this property. Tell me about this property. L is RE language. Tell me whether this property is monotonic or not. This L is RE language, this is monotonic property. This is monotonic. Why this is monotonic? Because if you take any RE language, remember, always take the elements from this domain. If you take any RE language L1 and you take any RE language L2, okay, so definitely you can see, if this is RE language, this is also RE language. So whether if this is superset, if this is satisfying this property, this is also satisfying this property. Actually this is trivial property. Okay, for RE languages this is trivial property. Every trivial property is a monotonic property. So if you have a trivial property, that means this is a monotonic property. Okay, actually I have seen some students, okay, this mistake they do. What they do, this mistake, like I gave them this, there is a friend of mine, I gave him this problem, whether this L is RE language, whether this is a monotonic or non-monotonic property of RE languages. This is what I asked. So actually we have to take, if you take L1 comma L2, if you take a counter example, remember in your counter example, both these things must be RE language. So okay, so here that is the point. Okay, do not take any not RE language, like do not do this. For example, this phi, this is a RE language, but if you take a superset of this phi which is not RE language, let's assume you consider this some not RE language, let's assume L is a not RE language. Of course this L is a superset of phi, okay, and this phi is satisfying this property, and this L, of course this L is a not RE language, so this does not satisfy this property. But this does not make this property non-monotonic. Are you getting my point? So my point is that always take elements from the domain. Okay, so always take in your counter example, always take two RE languages, L1 comma L2. Okay, now this is the point of monotonic property. Now this monotonic property, this Rice theorem says that any non-monotonic property is not even RE. If you have a non-monotonic property, then that is not RE. So for example, let's consider here. So you can see all these things. Is empty. This is actually non-monotonic property. You can see this is non-monotonic. Okay, so that's why this is not RE actually. This is non-trivial and this is non-monotonic. Because of non-trivial, this is undecidable. Because of non-monotonic, this is not recognizable. Not RE means not recognizable. Okay, not recognizable. Similarly, you can see this is a trivial property, and every trivial property is monotonic property. Okay, now this is infinite. This is a monotonic property. Is finite. This is non-monotonic property. Now what he is saying, so this Rice theorem is saying that if you consider this language LP, set of Turing machines, such that the language of the Turing machine satisfies this property P. Now if this property P is non-trivial, then this LP is undecidable. If this property P is non-monotonic, then this LP is not RE. So this is the point. But here you need to take care. If you have a trivial property means decidable, no problem. If you have a trivial property, then it is decidable, and if you have non-trivial property, then undecidable. So that's why you can say this is two-way basically. If you have trivial, then decidable. If you have non-trivial, then undecidable. Okay, non-trivial means undecidable. But if you have non-monotonic, then you can say not RE. If you have monotonic, then we cannot say anything. Okay, we cannot say anything. So this is the point. Now what if you have monotonic property, then how to check? So then we need to use something called this technique. We have Dovetailing technique that I will discuss. Okay, so with example, these things we will see. So let's take these examples. Accepts epsilon. This is a monotonic or non-monotonic? This is a monotonic property, because if you have RE language which is accepting which contains epsilon, then its superset also contains. So this is a monotonic property. Now this accepts infinite language. This is also a monotonic property. This is also monotonic. Okay, accepts finite language. This is non-monotonic. Because this is non-monotonic property, so actually this for this language you can say not RE. Remember, this language is not RE language. Okay, accepts a regular language. Tell me, accepts a regular language. This is monotonic or non-monotonic? Accepts a regular language. What is this, monotonic or non-monotonic? You can say this is non-monotonic property, because for example you can take like this is a RE language which is regular also, so this is satisfying the property. Now you can consider a power n b power n, this is RE language, but this is superset, but this is not regular, so this is non-monotonic property. And because this is non-monotonic, so this is not RE. Okay. Accepts the empty language, remember, not empty string. This is accept, there is a difference here. Accepts empty string and accepts empty language, there is a difference here. Accepts empty string means this empty string belongs to L of M, and accepts empty language means L of M is this, sorry, L of M is 5 empty language. So accepts empty language, this is again not RE, because this is non-monotonic property. This is non-monotonic property. Okay. Now let's see some more examples. Now here actually this is one interesting thing that I found. So monotonic means can't comment even about decidability. About decidability you can always comment. See, about decidability you can always comment. Why? Because I told you every trivial property, just all you need to do is check for trivial or non-trivial. If property is trivial, then decidable. If property is not trivial, then not decidable. So you don't have to worry about decidability. This you can always check using Rice theorem, as long as you can apply Rice theorem. Of course, Rice theorem has its own condition. You can apply it. Remember Rice theorem. The Rice theorem that we are seeing, this you can apply when you can apply. This you can apply in the case of Turing machines, in the case of RE languages. In these cases you can apply. Don't apply this Rice theorem in case of DFA, PDA, DPDA, CFG. In these cases do not apply it. Because Rice theorem is talking about properties of RE languages. Okay, so this is the first thing. Second thing, sometimes even in case of Turing machine also you cannot apply. When you have a property of RE languages, then you can apply, and when you do not have property of RE languages, then you cannot apply. So these things we will see in the next class. In tomorrow's class we will see this. Okay, but anyway, the point is decidability you can always check. And remember, trivial property implies monotonic property. So if you have a trivial property, automatically it is monotonic. If you have non-monotonic, then you can say that this is not RE. But if you have monotonic, then what to do? That we will discuss. Now this is a very interesting thing. This is interesting result that I found. So now let's see here. Accepts empty language. Yeah. So now I am saying that what is the difference between these two things? Accepting empty language. Okay, empty language. Okay. So if you have a Turing machine, this Turing machine is accepting empty language, and another line is accepting empty string. So you have a Turing machine, and for this Turing machine I am saying that this M is accepting empty language, this M is accepting empty string. What it means? In this scenario it means that LM is empty, because this M is accepting empty language, which means the language of M is empty. Now here he is saying that M accepting empty string, which means that empty string belongs to L of M. So this is the difference. Okay. Now, so yeah, this is the interesting thing that I found. So if P is a non-trivial property of RE languages, this we have seen so far, then of course this LP is undecidable, no problem. Okay, this LP means set of Turing machines whose language satisfies property P. Okay, so this is undecidable, that we have seen. But these two results are important. The first result is saying that, let's assume that you have already, see, checking for trivial and non-trivial property is very easy. Let's assume you have done it. So I am giving you a language. For example, let's assume I give you some language L, which has some set of Turing machines and some property. Okay, LM satisfies P. This type of language I give you. Okay, now what you do, the first task you will do is check for trivial or non-trivial. If this is trivial, then L is decidable. If this P is trivial, basically you are checking for P. If this P is trivial, trivial property of RE languages, because here we are concerned about RE languages. Turing machine means RE language. So that's why. If P is trivial, then you can say L is decidable. This L is decidable. Okay. Now, if this P is non-trivial, NT means non-trivial, then you can say L is undecidable. Now, in this scenario, if once you have checked that okay, L is undecidable, basically once you have already seen that this property P is non-trivial, in this scenario, I'm only talking about this scenario, basically this P is a non-trivial property. In this scenario, actually you don't have to check for monotonic, non-monotonic. Only thing that you need to check is whether empty language will satisfy this property or not. Okay, so basically you need to check whether this property is satisfied by empty language or not. Why I am saying this? Let's assume that empty language is satisfying this property, means P5 is true. Your empty language, this empty language, let's assume this is satisfying property P. What it means? It means this. It means that this P is automatically, it means that P is non-monotonic. How it means? See, because you know that phi is satisfying P, and this P is already non-trivial. I told you only in this case when P is non-trivial. In this case I am talking about. So this phi is already satisfying P and P is non-trivial. It means that there is some RE language who is not satisfying P. And of course you know that this this phi is a subset of every language. So this phi is subset of L also. So you can see that non-monotonic. So this P is basically non-monotonic property. Is it clear? So you can see actually once you have checked for non-trivial property, once you have done this, okay, trivial, non-trivial, this is very easy thing, trivial, non-trivial. Once you have done this, then you only need to check whether empty language will satisfy this property or not. If empty language will satisfy this property, then this property is definitely non-monotonic. You don't have to find two RE languages, one RE language is satisfying property, one RE language is not satisfying property. All these things you do not have to do. Just directly check whether this empty language will satisfy this property or not. If this is satisfying, then we can say monotonic, non-monotonic property. And of course, if you have a non-monotonic property, then this L is basically not RE. In this case, you can say L is not RE. What is the another situation? Another situation is if this empty language, if this empty language does not satisfy this property. Okay, if this does not satisfy this property, then what will happen? If your empty language, remember again, I am just repeating, only in this case of non-trivial. In this case of non-trivial, I am talking about. So in this case of non-trivial, your property is non-trivial. Now you check whether empty language is satisfying this property or not. If this empty language is not satisfying this property, then we have a very nice result, and that is he is saying that you just check whether this empty language is satisfying this property P or not. If this empty set is not satisfying the property P, then we will say that L is not co-RE. L is not co-RE. So co-RE language means if you have a language, this language is co-RE. Co-RE means L complement is RE. So this is the point. Okay, let me tell you some more things. Here actually, if you see, this is your, let's assume this is your set of decidable languages, means this is your recursive set. Here you have all the recursive languages. Here you have all the RE languages. And this is the area where you have not RE languages. This outer area, this is your not RE languages. So all the RE languages are, all the recursive languages, all decidable languages are here. Like empty language, like sigma star, all these languages like A power n, B power n, all these languages are here. All RE languages are here, and this is basically your RE but not REC. Okay, and this is your not RE. Now few things that you should note. The first thing that, let's assume you have a language here, means inside L. If you have a language here, then its complement will also be here. Because if you have a recursive language, then recursive languages are closed under complementation. So if you have a language L1 here, then the complement will also be a recursive language. Decidable complement is decidable. Second point, if you have a language here, means RE but not REC. If you have a language L2 here, then its complement will definitely be here. So if you have a language L2 here, then its complement will guaranteed to be here. Okay. Now the third thing, if you have a language here, then its complement either can be here or it can be here. Two situations. So if you have a not RE language, then its complement either can be not RE or its complement can be RE but not REC. So these are the situations, remember. So language here, then complement is also here. If language is RE but not REC, then definitely its complement is not RE. And if you have a not RE language, then its complement either can be not RE or its complement can be RE but not REC. Okay, so this is the diagram that we have. Now I was telling you co-RE. This co-RE language is a language, co-RE language L. This L is a language such that L complement is RE. So what you can say about L? Actually, you cannot say about L anything, because this is just saying that your L either can be here, because if your L is not RE, then also its complement is possible to be RE. As I told you, if your language L is not RE, then either it can be RE but not REC, or it can be not RE. Okay, but if your L is here, then definitely its complement will be not RE. So when I give you a language L, let's assume that I give you a language L. This is the language L given, and for this language I give you the information that this is co-RE. L is co-RE. Then what you can say? Then one thing that you can say with guarantee is that L complement is RE. This is the one thing that you can say for guarantee. The second thing, that if I give you a language L and I say that L is not co-RE, then what you can say? If L is not co-RE, then it means that L complement is not RE. So these are the things that you can say. Here, if L is co-RE, then you can say L complement is RE. Remember one thing, if L complement is RE, then definitely this, if L is undecidable, then definitely L is not RE. Okay, so this is the point. You don't have to worry about what is co-RE. You don't have to worry about it. I am just giving you these results because these results will help you here in this theorem. You can see. Remember one thing, this L is not co-RE. This will definitely tell you that L complement is definitely not RE. It will not tell you anything about L, but it will tell you about L complement. It will tell you that L complement is definitely not RE. If you have a language which is co-RE and undecidable, then that is not RE. Because if you have a language L, let's assume, and that is a decidable language, then you know that its complement is also decidable. So you can say L complement is also RE. So every decidable language is also co-RE. Because co-RE language says that, definition of co-RE language is that its complement is RE. This is the definition of co-RE language. Let me give you here all the results. I will give you here. So what we are going to do, you have a language first. Okay, you have a language L, and let's assume this language L is like this set of Turing machine such that LM has property P, satisfies property P. Okay, consider this L. If you have this type of language where set of Turing machine and LM satisfies P, if you have this type of language, then what is that you need to do? First, you need to check whether P is trivial or not. If P is trivial, then you can say L is decidable directly. L is decidable, L complement is decidable, because decidable complement is decidable. Second thing, if you find that P is non-trivial, if you find this P is non-trivial, then what you need to do? If P is non-trivial, then first thing you can say that L is undecidable. This you can say directly, L is undecidable. Undecidable means not recursive. Okay. The second thing is not recursive. Remember, not recursive. Now the second thing that you need to do is check whether empty set is satisfying this property P or not. Empty language 5. Empty language is satisfying property P or not. If this is satisfying property P, then you can directly say that L is not RE. You can directly say this. Okay. And if P5 means empty language does not satisfy this property, then what you can say that L complement is not RE. This is what you can say. Okay, so here you can say that L is not RE, and here you can say L complement is not RE. So this is enough. You don't have to worry about co-RE, po-RE, okay, whatever. Don't worry about them. This table is enough. If empty set, in this table you can see there is no monotonic, non-monotonic property, nothing, because this will take care. So you can see if P5 satisfy basically empty language satisfy property P, then you can directly say L is not RE. And if empty language does not satisfy property P, then you can say L complement is not RE. Okay. Now we will see Dove-Telling technique. What is that? So let's, okay, first we will check for all these whether these are monotone, all the things that we have seen. Let's apply them here. So help me out here. Tell me for first. Okay, or before this, actually let me give you some every actually decision problem. First of all, let me tell you what is a decision problem. A decision problem is a problem whose answer is in yes or no. So if you give me a problem P and its answer is in yes or no, okay, then this problem is called decision problem. First of all, this is the definition of decision problem. Now the second point is that decision problem, whatever decision problem you have, that decision problem corresponds to a language. Means for every language you can write a decision problem, and for every decision problem you can write a language. And how to do this conversion? Very simple. If you have a language like this, if you have a, let's assume you have a language like this. So if you have a decision problem like this, given W, okay, does W belongs to L? If this is your decision problem, then for this decision problem the language will be this. The language will be basically this: L is equal to W. Okay. So yeah, given W, does W belong to language L, then what you can say? You can say that L is basically W belongs to L. Yeah, so this is your problem P, and for this problem P, this LP is the language. So this is your decision problem. For this decision problem, this is the language, and for this language, this is the decision problem. For example, okay, let's take one formal example. Like he is giving, like here you can see, okay, all these examples we will see. Here he is saying that given a Turing machine, does LM contain M? Remember, this is a problem. This is a decision problem. Given Turing machine, does LM contain M? Okay. Now this problem I can convert into decision problem like this. What I will do, I will say that set of Turing machines such that LM contains M. This is how I will do. Okay, so let's take more example. It will be clear. So like if I ask you this, given DFA D, does LD infinite? So is LD infinite? So this is the question. This is the problem. Let's call it problem P. Then for this problem, what I am going to do, I am going to write a language L. And this language, what I will do, I will take those DFA for which the answer will be yes. So basically just collect all the yes instances. So how to create the language? Just collect all the yes instances. Collect those inputs for which answer is yes. Answer is yes. This is the point. Okay, like here you can see what you will do. Input is DFA. So if you give a DFA D1, and let's assume this DFA D1, for this DFA D1 language is infinite, then the answer will be yes. So what you do, you put DFA here, D1 here. Similarly for D2, if let's assume for D2 answer is no, then you do not put D2 here. For D3 answer is yes, then put D3 here, like this. So this I can also write like this. DFA such that LD is infinite. This is how I can do, such that LD is infinite. So this is my language for this decision problem. Okay. So is okay. Complement is not RE, then only we can't commit. Okay, so this is the behavior. Can you see this? You can see what is happening here. You have a decision problem. Okay, given DFAD is LD infinite. This is the decision problem. Of course, why this is decision problem? Because you can answer either yes or no. If I give you DFA D1, let's assume that the DFA, I give you this DFA, you check this DFA and the language is infinite, then what you will say? You will say yes. And as soon as you will say yes, I will put this in my language. Okay, so basically I am collecting yes instances. I am collecting those inputs for which you are going to say yes. I will give you D2. Okay, you will analyze the D2 and you will say that no, because let's assume that language of D2 is not infinite. Then I will not collect it. Okay, so basically those inputs I am going to collect for which the answer is going to be yes. So this is how from this decision problem I can create this language. Okay, so you can see for this decision problem, what is going to be the language? The language is going to be the yes instances. Yes instances of this problem are going to be the language. So the language will be set of DFA such that whose language is infinite. Okay, remember one more thing. Actually, languages are categorized into categories like regular, RE, recursive. These are the categories for languages. Okay, and problems are categorized in the categories like NP hard, okay, P, or you can say decidable, undecidable. So actually the point is this, that languages are not categorized into decidable, undecidable. Problems are not categorized into recursive, not recursive. But because for every decision problem we have language, and for every language we have decision problem. So that's why recursive languages are also called decidable. Decidable problems are also called recursive languages. So that is the point. Okay. So, but anyway, I just wanted to tell you that this is how you can convert decision problem into language and language into decision problem. From this language, you can also convert into decision problem. You will say that given a DFA, is language of this DFA infinite? So this is the point. Okay, now let's see all these problems. So for this first problem, I can say that set of Turing machines such that LM contains M. So this is my language. Now you can very easily analyze this language. First of all, you can see this property. This property is a non-trivial property. This we have already seen. Once this is non-trivial property, now just check whether empty language will satisfy this or not. You can see empty language will not satisfy this, because empty language of course has nothing. So that's why empty language will not satisfy this. And you know, when empty language does not satisfy, then what you can say? You can say that L complement is not RE. Immediately you can say L complement is not RE. But what about L? See, L complement is not RE, that is okay. But what about L? This is what we need to see. Okay, so this we will see in the Dovetling technique. Right now we will see. Okay, don't worry, just wait. Now let's take this example. Consider this. Now I am going to define the Dovetling technique. What is this Dovetling technique? This is basically a technique. If you see the English meaning of Dovetling, then you will see basically this is something like parallel. Okay, parallel. Okay, you can do things in parallel maybe, or you can say interleaving. Either you can call it parallel or you can call it interleaving. So what is this technique? That we will understand by this example. Let's assume I give you this language L, set of Turing machines such that this string, let's assume 0, 1, 0, this string belongs to LM. So this is our language L. Okay. Now for this language L, first of all you can see this is a non-trivial property. Second, you can see this is non-monotonic property. This is monotonic. This is monotonic property. You can see this is non-trivial property and this is monotonic property. And of course you can see that this empty language does not satisfy this property. So for empty language, this does not satisfy this property. I can guaranteed say that L complement is not RE. This I can say with guarantee. Okay, L complement is not RE. But what about L? So for L, we are going to use the dovetailing technique. This is parallel interleaving. What is this behavior? See, now you need to understand all your concepts that you have basically you have understood in today's class so far. You need to apply them, nothing else. Dovetailing technique is nothing but just a definition of Turing machine. You need to apply the definition of Turing machine. Okay, because what I am going to do, let's assume that this is, for this language I have a Turing machine. Let's assume that. So for this L, assume you have a Turing machine. Okay, so this Turing machine, let me call it M dash. So this is my Turing machine M dash. Remember, this Turing machine I am assuming for L. Okay, this is I am assuming for language L, not for this LM. No. Okay, now what this machine is going to do, this machine is going to take a Turing machine. So this machine is going to take this M, because the input is this M. So my Turing machine is M dash, and this M dash is for this L. Okay, and the input to this M dash is this M. Now assume that you are giving me, basically this is me. Okay, you are like I am that Turing machine, I am this M dash. Okay, now what you are doing, you are giving me this M, which is a member of L. Basically you are giving me a Turing machine which will satisfy this property, So this Turing machine M that you are giving me, this belongs to my language. Okay, can you see this? So that is the point. Now this M belongs to my language L. Now what should be my behavior? My behavior should be that I should be able to halt and say no, say yes. This is my behavior. Let me check whether I can do this or not. What I will do, because you are giving me a Turing machine, so I will take this Turing machine, I will take this M, okay, and I will run this M on 010. I will run this M on 010. This is what I am going to do. See, I am standing here, you are giving me M. Okay, now what I am going to do, I am going to run this M on 010. Now what will happen? Because you already told me that M belongs to L, means this Turing machine L, this Turing machine M belongs to this language L. So it means that 010 belongs to LM, means this 010, this belongs to LM. And now remember, the definition of Turing machine says that this is your Turing machine, this is your string, and string belongs to the language of the Turing machine. So this M will definitely halt and say yes. So this is guaranteed. That this will definitely halt and say yes. And as soon as it will halt and say yes, I will also halt and say yes. Because this is halting and saying yes. Okay, so I will also halt and say yes. So one thing you can notice, that if you give me a member, remember, if you give me a M which belongs to my language, if you give me a member, if you give me a Turing machine which satisfies this property, then I will be able to halt and say yes. The proof is here, you can see. Because what I will do, whatever Turing machine you will give me, whatever member Turing machine you will give me, I will run it on 010. And because the definition of Turing machine says that this Turing machine M, this internal Turing machine M, this will halt and say yes, so I will also halt and say yes. But remember, why this is, so yes, this definitely this language L is RE actually. This is RE. So you can say that L is RE, because you can say why this is RE, because I can halt and say yes for the members. For the members I can halt and say yes. This is the point. Is this point clear? Let me know. Now let's also see why this problem is not decidable. Like what will happen if you give me a non-member? If you give me a Turing machine, let's assume let's assume M2. If you give me a Turing machine M2 which does not belong to L, let's assume. Yes, what you are saying, that is we are going to discuss. Like see, if you give me a Turing machine M2 which does not belong to L, what it means? It means that in this Turing machine M2, this Turing machine M2 does not accept 010. So what I will do, I will take your M2, this M2 I will take, and this M2 I will run on 010. But now, if you remember the definition of Turing machine, remember this 010 does not belong to LM2. Means this 010 does not belong to LM2. So what is the behavior this M2 will give you? The behavior of M2 for this string 010 will be may or may not halt. So that is the difference here. Here this will definitely halt and say yes. Because this will definitely halt and say yes, so I will also halt and say yes. But now if you are giving me M2 which does not belong to my language L, means your M2 does not accept 010. So now this M2, when I run this M2 on 010, then what will happen? Then this may or may not halt. This M2 may go in infinite loop. Let's assume this has gone into infinite loop. Let's assume. Now I am waiting. But this has gone into infinite loop. So you can see that I am continuously waiting. Okay. I don't know whether it has gone into infinite loop or not. That I do not know. Inside it may have either it may have gone into infinite loop, or maybe it is computing. I do not know. But the point is that now I cannot I cannot guarantee that I will be able to halt. So that is the point. So Naim, did you get it? So this is the point. Okay, so let's take more examples. It will be clear. These are now let's see the like so far there was no dovetailing technique involved. Now let's see dovetailing technique. Okay, let's take this example. Let's consider this language set of Turing machines such that you can say cardinality of LM is greater than or equal to 5. Let's take this. This is your language L. So what you can see, the property is basically that the language cardinality is greater than or equal to M. Means this Turing machine accepts at least 5 strings. You can say this Turing machine accepts at least 5 strings. Okay. Now you can notice that first of all this is a non-trivial property. Now, so because this is a non-trivial property, you can say that L is undecidable. Remember, this L is undecidable. Okay. Now the second point, you can see this is monotonic property. Monotonic property. You can notice, because if you have a RE language which is containing at least 5 strings, then its superset also will contain at least 5 strings. So that's why this is monotonic property. Now let's check whether empty language will satisfy this or not. So whether this property means containing at least 5 strings, this property. What is this property? If you remember, this property, if I write, property is basically containing at least 5 strings. This is the property containing at least 5 strings. So now let's see whether empty language will satisfy this property or not. You can notice that empty language does not satisfy this property. So from this you can directly say that L complement is not RE. L complement is not RE. Okay. But what about L? We want to find out about L. So what I am going to do, see, this is what I am going to do. You notice one thing, that now what I am going to do, this is me. So this is my M dash. Let's assume that L is RE. Of course, I don't know whether this L is RE or not, but I am assuming that L is RE. So I should be able to halt, guaranteed. Can I guarantee that I will halt and say yes for members? This is the only point. Can I guarantee that I will halt and say yes for members? So let's assume this is my M dash. Okay, and let's assume L is assume L RE. If L is RE, then I have M dash, and this M dash, what it will do, if you give a member, means if you give a M which belongs to L, means if you give a Turing machine whose language cardinality is greater than or equal to 5, then what will happen? What I will do? See what I will do. Now you just notice what I will do. This is interesting. What I am going to do, there are 2 things that I can do. Okay. The 2 things are like this. If I have these strings, because, like, of course, these are the strings 0 1 0 0 basically. Okay, this is 0 length string, 1 length string, okay, 2 length string, and so on. Like, these are the strings you have in the sigma star. These are the all the strings. Now I need to check what I need to check. Just, okay, see, intuitively, just common sense, just use the common sense. If you give me a Turing machine, and for this Turing machine I want to see whether to accept or not, then what I have to check? I have to check whether this Turing machine will accept at least 5 strings. I don't know what are those 5 strings. I do not know. Okay, so I just want to see whether it will accept at least 5 strings or not. So one very naive way, what is very naive way? The very naive way is this. What I will do, I will take this Turing machine M. Of course, this is me, and I will take this Turing machine. I will take this Turing machine M that you are giving me. Okay, and for this Turing machine, what I will do, I will give it first. I will give it epsilon. Okay, after, if this Turing machine accepts epsilon, then I will just increase my counter. I have a counter here. Okay, I have a copy pen, and if this M accepts epsilon, then I will increase my counter, because I want only 5 tick marks. If I get 5 tick marks, then I will accept this M. But why this is a naive approach? This naive approach is because, let's assume that 0 does not belong to LM. Let's assume you are giving a 0, you are giving this 0, and let's assume that 0 does not belong to LM. Then what will happen? Then it will happen that maybe this M can go to infinite loop. So I am waiting. I have a copy pen in my hand. I am waiting. But this Turing machine M has gone into infinite loop on 0. Now I will just keep on waiting, keep on waiting, keep on waiting. So that is the problem here. So of course, this way, this naive approach, this is a very naive approach. Now what I am going to do, this approach I will not apply. I will become smart. Now I will apply parallel processing. Okay, this parallel processing I will apply. What I will do, so this is me. Now you are giving me Turing machine M. So what I will do, I will take all these strings, empty 0 1 and 0 0 0 1 1 0 1 1. Okay, and of course 3 length strings, 4 length strings, and so on. You can notice that what I will do, first I will take this string and I will run this Turing machine M for this string for one step. So you can see, for one step only, means only one transition. One step means one transition. And after one transition, I will see whether this M is accepting empty string or not. If yes, then I will increase my counter. I have a counter. I am standing here. I have a counter. I will increase my counter. Basically, I will increase my tick mark. But after one step, what I will do, I will take this 0 and I will run it for one step. So basically, I will run it for one step. Then if this after this one step, if this is accepted, then that is okay, that is very fine, that is very good. But if it is not accepted after one step, then I will run this 0 for one step. If this 0 is accepted in one step, then that is fine. Okay, but if it is not accepted in one step, then what I will do, I will run it 2 step. See, this epsilon I have already run for one step. I will run it for 2 more step. Okay, again now, if this epsilon is accepted, then I will put a tick mark. But if this, in these 2 steps, total 3 steps, 1 and 2, total 3 steps, in these 3 steps, basically if this is not accepted, then I will go to 0 and I will run it for 2 steps, and I will go to 1 and I will run it for 1 step. Now what I will do, I will again come back to epsilon, I will run it for 3 steps, okay, and again I will run it for 3 steps, I will run it for 2 steps, I will run it for 1 step. So are you seeing what I am doing? Then I will run it for 4 steps. It will this I will run for 4 steps. This I will run for 3 steps. This I will run for 2 steps. This I will run for 1 step. This is how I am going to do. Now in this technique, what is the benefit I am getting? See, this is called Dove-Telling technique. Okay, but what is the benefit that I am getting in this technique? In this technique, the benefit is this. Let's assume you know that you are giving me a Turing machine. Okay, if you give me a member Turing machine, like if you give me a Turing machine M, which actually basically accepts at least 5 strings. So this M that you are giving me, this is a member. Okay, and this is actually accepting at least 5 strings. Let's assume those 5 strings are maybe one string is 0 power 1500, of course you can say. Another string is maybe 0 power 1 lakh, 1 billion, let's assume 1 billion. Okay, and another string is 0 power 1 billion, 1 power 1 billion, like this. Let's assume these are 5 strings, or another string is 0 0, and one more string you need, so one more string maybe 1 power 2000. Okay, 1 power 0 power 2000, like here. So let's assume, so you are giving me a Turing machine M, and this Turing machine M is a member. So basically you are giving me a member of me. Okay, I am the Turing machine, and I am taking this M, and let's assume this M already accepts at least 5 strings. At least, of course, there may be many other strings, we do not care, but at least 5 strings. Let's assume these are the 5 strings. Now, in this technique, what is happening, in this dovetailing technique, what is happening, that I will never stop at one string. Okay, I will just keep on going on. So I am starting, okay, I started with epsilon, one step, then this 0, one step, two step, okay, you know how it is going. So ultimately what will happen, ultimately I will reach to 0 0. After some finite amount of time, only finite amount of time, I will reach 0 0. And eventually, because the behavior of Turing machine says that this 0 0 already belongs to LM, so definitely it will halt. After some point of time, it will definitely, some finite amount of time, it will definitely halt. Similarly, after finite amount of time, I will again reach 1500 also, 0 power 1500 also. So again, it will also halt. So you can notice that within some finite amount of time, I will be able to find these 5 tick marks that I want. I want 5 tick marks. I will get those 5 tick marks after finite amount of time. And remember one thing, in this naive approach, what was happening? In this naive approach, this string which does not belong to M, because of this string, I was going into loop. So I was stuck here. I could not go further. But in this new approach, in this dovetailing approach, you can see I will not be stuck at any string on which I can go to loop, because let's assume that on this string 0 I can go to loop, but I am not going to dedicate my whole time to 0. What I'm going to do, on this 0 I'm going to run for only finite amount of time, then I will move on to something else. So that is the reason you can say I can for the members I can definitely say yes. Okay, so you can see, for the members, if you give me a member, then within some finite amount of time, eventually I will be able to accept all these. Eventually, within some finite, maybe it can take 1000 years, I do not care. It can, because 1000 years is also finite amount of time. So you can see, within some finite amount of time, I will be able to say yes. I will be able to halt and say yes for my members. And because I am definitely guaranteed to halt and say yes for members, so I can say this language is RE. So this language that you have, this language L, this is RE. So L is RE. So I hope that this example is clear. Let's take more examples, okay, to understand this. As take this language L equal to set of Turing machines such that LM is infinite. Take this, LM is infinite. Now, first of all, you can see this is a non-trivial property. Because this is a non-trivial property, so you can say not REC. Okay. Next, you can see one more thing, that this is a monotonic property. Next, you can see that this is a, let's check this empty language. So empty language does not satisfy this property P. Okay, property P is not satisfied by empty language. Empty language is not infinite. So I can guarantee that L complement is not RE. This I can guarantee. But what about L? So now let's check for L. Again, I will try to use the dovetailing technique. But will the dovetailing technique work? See, this L, in this L, I have those Turing machines which accept infinite language, means infinite number of strings. So even if I use dovetailing technique, I will have to spend infinite amount of time. Because you can see, even if I do this epsilon 0 1 0 0 0 1, okay, all these strings, Even if I use this dovetailing technique, then what will happen? I will have to spend infinite amount of time because there are infinite strings. Okay, so let's assume these are the strings like 0 0 0. Let's assume all these alternative strings, let's assume all these alternative strings are accepted by this by this Turing machine M. Then in that case also you can see that I will have to spend infinite amount of time. Whether I use dovetailing technique or not, that does not matter. I will have to spend infinite amount of time for one Turing machine. Like this is I am standing here. Okay, I am a Turing machine, and my language is L. I am assuming that L is RE. This is my assumption. If I am assuming that L is RE, then definitely I have a Turing machine. In this Turing machine, if I give a, let's assume I give a member, means if I give a Turing machine M whose language is infinite, then can I give a guarantee that I will halt and say yes? No, I cannot guarantee. Why? Because even if I use this dovetailing technique for M, then also I will take infinite amount of time. Okay, so that is the reason this language L, this is not RE. This language L is not RE. L complement is also not RE. L is also not RE. So anyone has any doubt, you can ask. We will continue tomorrow, but if you have any doubt, then you can ask. So tomorrow it will be more clear because actually tomorrow we are going to take just examples, no theory, just examples. Many examples we will do. Okay. So if anyone has right now, if anyone has any doubt, then you can ask. At this moment, if anyone has any doubt in today's lecture, then you can ask. And remember, in tomorrow's lecture we are going to do many examples, like back to back examples for 2 hours. All the previous year GATE questions, all the previous year TIFR questions, all these things we will do. Okay, so this complete chapter will basically, this decidability chapter, you will not do anything wrong in this chapter, that I can guarantee. So if you have any doubt anywhere, then I would suggest that you just rewatch this video. Okay, and let me just tell you this dovetailing technique one more time. Just an informal description of dovetailing technique. What is this doing? In this dovetailing technique, or you can say basically parallel processing, in this what we are doing like this. You have a Turing machine M. This Turing machine M, we are running it on the strings W1, W2, W3 and W4 and so on. So let's assume these are the strings. So what we are going to do, we are going to run this Turing machine M for W1 only for one step. Then what we are going to do, then we are going to run this. So after this one step, what we are going to do, we are going to run this M on W for one step. Then we are going to run this this M for W1 for 2 more steps. Basically total 3 steps. Total 3 steps. Okay. Then what we are going to do, we are going to run for this W2 for 2 more steps and then W1 for 1 step. Okay. So then this for 3 more steps, total 6 steps. Okay. Here 3 more steps, here 2 more steps. Here 1 more step, like this. So like this we are going to do. So in this way what will happen, let me tell you. In this way what will happen, first of all, let's assume this string, on this string, let's assume this M will go to infinite loop. If you run this M on W1, let's assume you will definitely go to infinite loop. But we don't have to worry about this infinite loop in this scenario. Why? Because I am not running my M on this W1 dedicatedly. That is not what I am doing. On this W1, I am not running dedicatedly. Okay, I am going to other things also. Now let's assume this is causing loop. Let's assume this will cause loop. Let's assume this will cause halting and accept. Let's assume this will basically accept, and let's assume this will reject, basically halt and reject. And let's assume this is also loop, and let's assume this is also accept. remember, because this is accepting, so after some finite amount of time it will definitely accept. Maybe let's assume maybe 100 steps, maybe 100 steps. So you can see that after some finite amount of time, on this w I will reach total 100 steps, after some finite amount of time on this w I will definitely reach 100 steps. So at this point of time I will accept this w, and I will basically at this point of time, within some finite amount of time, I will get to know that okay, yes, w2 is accepted. Remember, even though remember, this w1 is causing loop, but we are unaffected of loop because we are not running this w1 dedicatedly. Now let's assume this is rejecting but halting. This is rejecting but halting. Let's assume after 50 steps, this is halting. When it will halt, then we will check. This will halt, we will check whether this is halting in state, final state or reject state. If this is halting in reject state, then we will basically remove it from the computation. Now we can remove it from our computation. Now okay, now we will not run on this w3. Similarly, we will remove this w2 also. Okay, now if this w4 is looping, then also we do not care, because ultimately on this w1 I will definitely reach some number of maybe after 1000 steps. So ultimately after some finite amount of time I will guaranteed I will reach 100 steps. I will definitely do 100 steps on w5, and then I will accept this w2 w5. So that is the point. This is our dovetailing technique. We are not spending our dedicated time on any string. Okay, we are doing it parallelly. You can think like this, we are doing it parallelly. So either you can think like this, this dovetailing technique, either you can think like this, or you can think like this parallelly. Basically we are doing all these things parallelly. Okay, so that is the point. No, but okay, this is this is the actual method. This is a formal method. Do not think parallelly, think interleaving. There is a difference between parallel and interleaving. Parallel means two things are happening at same time, and interleaving means one thing, then second thing, third thing, second thing, like this. So interleaving. So this is called interleaving, this is called parallel. So you can think in an interleaving. This is an interleaving fashion. Yes. So Jairam, we are done with the theory. There is no theory required now. In the next lecture, all the questions we will do. Everything that we will see, all the questions. No theory, nothing. Okay. So if anyone has any doubt, you can just re-watch the video wherever you have doubt. In whichever part you have doubt, just re-watch and you will get it. Okay. For at most 5 strings. That is non-monotonic property, you can directly apply. Okay, like UJFI is asking this. UJFI is asking this question. Consider L set of Turing machines such that M accepts at most 5 at most 5 strings. Okay, so this I can write like, see, first of all, this I can write like this. I can say that LM cardinality is less than or equal to 5. This is how I can write. So one thing you can notice, this is a language property. First of all, this is a language property, because this statement I can write like this: LM cardinality is less than or equal to 5. Now you can notice one thing, that first of all, this is a non-trivial and non-monotonic property. Non-monotonic property, so automatically this L is not RE. So this L is not RE. So here actually you don't even have to apply non-dovetailing technique and these things. You don't even have to apply. Now, but okay, let me give you, you might be wondering why we cannot apply this dovetailing technique here. Like why this dovetailing technique will fail? Because we only have to check for 5 strings. So let me tell you why this. Let's assume these are the strings. Okay, epsilon 0 1, okay, 0 0 0 1 1 0 1 1. Let's assume like this, and I am here. I am putting tick mark here. So I am standing. I am the referee, and I need at most 5 tick marks. So basically, if you are giving me a Turing machine M, for this Turing machine M, I am checking whether it is accepting at most 5 strings or not. Then what is the problem that will happen? See, this is the problem that will happen. Let's assume that L of m is this. Let's assume epsilon 0 comma 1 comma 0 0. Let's assume this is the lm. So you can see that this is a member, because the m is accepting at most 5 strings. So first of all, you can see m is a member. So I should be able to halt on m. I should be able to halt and accept m. This is what I should do if I'm a Turing machine. Okay, if I'm a Turing machine for this language L. Now see what will happen now. Of course, for this string, if you apply the Dover-Telling technique, of course you will halt for this string after some finite amount of time. For this also you will halt, for this also you will halt, and for this also you will halt after some finite amount of time if you apply the Dover-Telling technique. But after halting for these 4, now we cannot stop, because we want to make sure that at most 4 strings are accepted. This is what we need to ensure. So because we need to ensure this thing, we cannot stop anywhere. We will have to check all the strings. Okay, we cannot stop anywhere. We have to check all the strings. So that is why you can say we cannot stop in some finite amount of time. We need infinite amount of time. So that is why here you can say that even for members I cannot halt in finite amount of time. Even though this m is a member, but I cannot halt within finite amount of time for this member also. So that is the reason this is not RE. This problem is not RE. Okay. So yes, of course you can apply Rice theorem. You can apply, but the point is that this understanding is important. That you why for this language L, like for this language L, why we do not have Turing machine. This understanding is important. Why we do not have Turing machine. So because if we have Turing machine, then that Turing machine, like if we have a Turing machine m dash, then that Turing machine cannot stop anywhere. It cannot stop at within some finite amount of time. It will have to check for all the strings. So that is the reason. Okay, so anyway, let's see the remaining things in next lecture. Let me know your feedback, and if there is few things that are unclear, if some things you found hard or something like this, okay, then just wait for the next lecture. In the next lecture, with the help of example, all these concepts will be over. Okay, so just wait for the next lecture. After the end of the next lecture, you can let me know whether you got complete decidable, basically whether you are able to solve all the questions of decidability or not. So that is the only concern. You should be able to solve all the GATE, TIFR, all the questions of your test series, whatever. All those questions you should be able to solve. That is the motive for this class. Okay. So see you tomorrow. Thank you everyone.